Okay, so tonight we're going to be moving on to module number 5. And in module 5, let's start looking first at the learning plan here. In our learning plan, you're going to notice that we go back to the e-textbook, the McGraw-Hill that we have been using up until module 4. We went out of the book with a handout, and now we're going to be back in the book. And not to make anything confusing, but these are going to be chapter 4 problems. So our module 4 was chapter 4 out of a different book, and our module 5 is going to be chapter 4 out of the McGraw-Hill. Okay, so so we're going to be kind of referring back to that one. You'll notice that the sections that we're going to be looking for, I have identified here. There is a guided notes here. All right. I have it printed out for those in class, but if you are virtual and you want to print this off and follow along, you can do so. But otherwise, if you aren't able to print, that's okay. Just take some good notes. And so I know where the fill in the blanks and all that kind of stuff is, because this is going to be what you hand in for the practice problems. Okay. And then the practice problems are listed down here below. All right. And those are in the handout. So you don't really have to worry about, doing those. We'll do them right along with us. You'll be doing them right along with me in class. Then you'll notice there is a connect. There's a connect for module 5 because we are going back out of the textbook. And then you'll notice as well that there's going to be the practice problems that we just talked about and application problems. I'm just going to go out really quickly to the module. You're going to notice that the connect is here. Practice problems are here, and then application problems. So if we click on the application problems, I started listing them rather than a PDF. I thought, why don't I just list them here? I think it's easier than having to click open a PDF and all that kind of stuff. So, so I do have the answers here as well. There's 8 problems, so they're 10 points each, and they'll mimic the practice problem that we'll be doing in class. So that is that. Any questions before we get into things? All right, then what we'll do is we will get started. I'm going to go underneath my camera, and we're going to start by looking at our handout, okay, or our guided notes. And you're going to notice here in chapter 4, module 5, we're talking about equilibrium of rigid bodies. Now, we've talked about equilibrium already. We talked about equilibrium back in module 3, but it was of concurrent force systems. And that was when we had either an application point that was common between however many forces we were looking at, or if we would move them along their line of action, there was an intersection point that was common for all the forces. That's not the case here, okay? So when we're equilibrium of rigid bodies, we actually are going to have things that are offset. So when we had done module 4, we got introduced to the concept of moments. And that was really the big purpose in module 4, so that now we can continue to use them, but use the condition of equilibrium to solve for unknown forces, whether they're applied forces or if they're forces at the reaction or at the supports and which would be reactions. So, so that's the main focus here. We're going to be back in equilibrium. And so there's a fill in the blank here. It says when the forces and body are in equilibrium, all the forces and the moments are equal to 0. So we're going to fill this in with equilibrium. Okay. And there are now 3 equations of equilibrium. The first 2 we used back in module 3. So the first 2 were sum of the forces in the x equals 0. Okay, so everything has to balance out. And then the other one was sum of the forces in the y equals 0. So we were just looking vertical and horizontal. And we used our convention to determine what was positive and negative, okay? But now, because we know about moments now, we're going to also set any moments about a point or an axis. And I'm going to put this little cloud right here. That means that we have to fill that in to identify where we're summing our moments around. And we're going to set those equal to 0 as well, okay? Now, we called it the new convention in module 4, but it's really no longer a new convention. It's a complete convention. And that convention is going to continue to be positive going to the right and up for forces. And then counterclockwise rotations generated in our moments are going to be positive as well. Okay. Now we got some experience in the last couple chapters or in modules, making free body diagrams. Okay. Now, I don't know, I'm just going to talk in general, I just want to kind of get your ideas. Free body diagrams, what do they mean to you? And what is included in a free body diagram? And we'll kind of list things here. When you think about free body diagram, we've talked about them and we've done them. What are we doing with those? Like, what's the purpose and what do we include? Anyone? Go ahead.
I'd say simplifying the forces on something.
Yeah, simplifying. Yeah, simplifying like forces on a body. And that makes sense because we kind of strip down and we simplify what the drawing looks like, right? So a lot of times we might have thickness to something like a beam or a rod, but we don't show the thickness. We just represent it with a straight line. Like it's just that, right? And then we'll add some distances and points and stuff. Yeah. So we simplify it. It might not even look very much like the body at all, but it's a simplified version so that we can then calculate the things that we need to. Good. What else do we know about free body diagrams or what's included in them? Magnitude of what? And what do the vectors represent? Forces. Yes. So we're gonna represent forces. And we have to know magnitude, right? Direction. Absolutely. Yes. And that's why it becomes really important now that we put arrowheads on our vectors, okay? Because we literally need to know where they are, where they're being applied, and in what direction. Okay. What else would we include on a free body diagram? I think we got the purpose. Yeah, convention. Yep, include your convention. Yep, we have to know what's a positive, negative, right? Both in the direction of the forces as well as the rotations. Yep, convention. What else? Yeah. So points, important points, right? Or axes. So yeah, when we label something in A, B, C and such, right? Yep, we have to kind of know and we can see what's going on. What else? Go ahead. Units, absolutely. Units. For both forces and what else? Distances. Yes, we need the distances of the stuff over here, right? Where the points are, where the forces are. Absolutely. Anything else that you can think of that we would include in our, I'm going to open up the chat in case anybody has anything there. That we would include on a free body diagram. So yeah, a free body diagram is a simplified version of something that has forces on it. We're going to put the forces where they need to go, making sure that we have the magnitude and direction of them. The convention is going to guide us. So then when we start solving for unknowns, potentially, we know, which direction is going to be positive and negative. We're going to have to identify points and axes that are important. And then the units that we're working in for both forces, but also distances, right? Also distances. Good. I think that's pretty complete. So, so we're going to start looking now at reactions for two-dimensional structures. Okay. Now there are common types of supports. There are common types of supports, and those are listed for us on page 160 in our book. So I have that here. So if you go into the book, 160 is going to be a place where we're going to be referencing back. Okay. And what I want to show you is the most common types of supports and what they're going to look like, but then also how we represent them in a free body diagram, for instance. Okay. So the first type that we have here is a roller, a rocker, or a frictionless surface. Okay. All of those types are only going to have one reaction force at the support. Now, why would it do that? It's the one direction that it's going to be what we call constrained. So as we look at a roller, for instance, a roller is going to offer the ability to freely move. If you look at these as a horizontal surface, freely move back and forth horizontally. So it's not constrained there. It can move. But in order for it to actually be supporting, it needs to be in contact with the surface, right? Now, this type of a roller, you would expect that the support then is going to push back up. What is the body is like this portion right here. The roller is the green part. The body is the gray, like section that's going up and to the right slightly. And we would push up as a support on that body. When we have a roller like this one is constrained up or down. So that means that its one support may go down or it could go up. All right. It just depends on what the, arrangements and the forces that are there. Okay. A rocker, this is going to be one that we're going to be pointing towards the body because this has to be in contact for it to actually support. If it's not in contact, if it's off the support, well, then it's not supporting. And then a frictionless surface. This too would be one reaction going perpendicular to the surface that it's riding on. And then this one is going to be pointing towards the surface. The only way that the surface is supporting is if they're in contact. So if it's not in contact, if it lifts off, well, now it's not supporting anymore. Okay. So any one of these scenarios is one unknown force, always perpendicular to the surface that it's riding on. Okay. So if we look here in this second part, you're going to notice that on number 2 for rollers, there's going to be one reaction perpendicular to the surface that it's riding on. Okay. I didn't put them in order. I put them in the order when I did it in what I was thinking, not in the order that's here. And then there's another one on the next page. A frictionless surface, which is the other one in that very first category, is going to also have one reaction, but it's going to be perpendicular to the surface it's riding on, and it's going to point towards the body because it'll be in contact. Okay. So that's our first line there. Now, as we go back to page 160, the next ones in the next row below here, you're going to notice that they have a cable and they have a link. Okay. Now the cable is kind of like a rope or a cable. When it's supporting properly, it's in tension, meaning that it's going to pull away from the body. Okay. Because if it's not in tension, if it's collapsing, it's not supporting, right? Because it's just the nature of a rope or a cable. On the other hand, when we have a rigid link that is, of substance, like, that's made out of metal or something of the sort, if we pull on it, okay, that'll support. And if we push on it, it'll also not collapse. It will support. So in this case, this one can actually point towards or pull away from the body. But in both cases, the force will be along the cable or along the link. So if this is at an angle and not vertical or horizontal, then it's going to be along the length of that cable. And as you can imagine, we're probably breaking it into components to deal with it. Same thing with this rigid link. If this rigid link is not vertical or horizontal, that force is going to be along that rigid link, and then we would break into X and Y's if we needed to. Okay, so for a cable, it's also going to be one reaction pulling away from the body along that cable. And then for a rigid link, one reaction, again, along that link, but depending if it's towards or away, if it's in compression or in tension, will determine if it's pulling away or pushing towards. Okay. The next one is not going to be a common one that we see very often, at least at this point in the class. All right. And this is going to be a frictionless pin in a slot or a collar on a frictionless rod. Not that they can't be used and that they're not used. They are used. We're just not going to hit them in this chapter. We're going to hit kind of the more common ones. But this would be perpendicular to the actual rod itself or perpendicular to the line of action that it would be on. Okay. And then as we move down, the last two are going to also be two that we're going to see on a more regular basis. The first one that we're looking at here is called a pin reaction or a frictionless pin. A frictionless pin is going to have a pin through here. So it's going to constrain going horizontally and vertically. So there will always be an X and a Y component for a pin reaction. Always. Do you have a question, Christian?
No.
Oh, okay. Okay. Gotcha. And then the other one that's in this category, because it also has two reactions, is going to be a rough surface. The rough surface is going to be perpendicular to the surface, but then also because it's a rough surface, there's going to be a friction force. We won't see the friction in this chapter because we actually spend time on a separate module for just friction. So we will see it there. Okay, but both of these have two reactions. So you're going to notice if we go back to the beginning of this section, a pin is going to have two reactions, one in the X and one in the Y. And then when we turn the page to the very last one, a friction on a rough surface is also going to have two reactions. One is going to be perpendicular to the surface that it's riding on, and the other one is going to be in the opposite direction, 90 degrees to that, in the direction impeding motion. Okay. And then our very last one is a fixed support, and this one's going to have three reactions. It's going to have the ability to constrain in the X, the Y, and a moment. Now, a fixed support is going to be something like what we see here, okay? And all of the support is on one end, and the other end is free. And that other end, or along the length of in this case, that post or that beam, it's going to have some forces that are on it. And then we have to determine down here what's going on. So this doesn't allow it to move horizontally. It doesn't allow it to pull out vertically. And because of the nature of this offset force causing rotation, it has to be able to resist that rotation going in the opposite direction as well. Okay. So that's why there are up to three reactions for a fixed support. Three reactions for a fixed support. So page 160 is a great representation of all of the common support types and how many reactions they're going to have. I'm going to continue to pull those back, and as we do problems, we'll get lots of different looks at this. Okay. All right. Now, most of the problems that you're going to be solving, you're going to either be solving for unknown forces and reactions at the supports. And usually the most common is going to be reactions to the supports. We identify what the applied loads are, and then, okay, what has to happen at the reactions of the supports. So when you're, for instance, later on designing shafts, and we're going to see the forces that are on the shafts that have to be supported by bearings. Those bearings are supports, and we have to figure out what are the forces that those bearings have to see so that we can properly size those. That's going to be in machine design elements. Okay. So, so you get to do that. That's going to be fun. And we'll revisit statics at that time and be like, remember when? And you're gonna be like, well, yes. So it's good. So the process that we're going to go through, it's a pretty short process. There's really two main steps. I don't know if this is really a process, but two steps. First of all bodies are assumed to be in equilibrium. So we're going to be using those three equations of equilibrium. And we know those to be some of the forces in the X equals 0, some of the forces in the Y equals 0, and some of the moments around a point. I'm just putting a little cloud there because we're going to identify that point based on our free body diagram. Those have to equal 0 as well. So we're going to, in our first step, we're always going to draw a free body diagram. And what else are we going to add at that point? The convention. Yes, the convention. Okay. Always on each one of our individual problems. We're not doing it for a set of problems. We're doing it for each problem.
Quick question.
Yeah.
So, like, for the last assignment, we had to draw multiple free body diagrams per question.
Okay.
We just have to add it once per question, or just every single.
Is that for 4?
Yeah.
For application? Oh, I gotta remember, what is the problem?
It was just the one where you draw the free body diagram at the beginning and you do it at the end. With the result.
Oh, like the position of the rows. No, just once for that problem. Yeah, so on those, the question that Jack had was, you have us draw another like diagram showing our, what the answers meant that you solved for, like the magnitude of the resultant and or X and Y components, and then where it's located with respect to the point that you summed around. And Jack's question was, do I need one for the beginning of the problem and for that at the end? The answer is no, just once for the whole problem. Yeah, good. Then as we look here, when we draw our free body diagram, we want to make sure that we add all of the forces of the applied loads. Okay, so the applied loads are going to be things including the weight of something or any applied forces that are given to us in the problem. Anything that has a known magnitude, any unknown variables, sometimes maybe it's solving for that, so that, or a distance, and then you want to put in any dimensions and labels that are there. And then the other part of it is you're going to add all of the reactions at the support. So you're going to recognize, okay, what's the support that's, you know, at this location. And then I'm gonna go back to my page 60. I'm gonna look there and I'm gonna be like, all right, if it's a roller, I've got to put 1 force here. If it's a pin, I've got to put 2. If it's a fixed support, and so on. So it's gonna be really kind of reading those diagrams and making sure that you are putting the appropriate, you know, supports in place. Then, and then we're gonna add the vectors to represent those reactions to the supports. And then you're gonna find out, I'm gonna say this quite often, you're gonna assume a direction if it's not obvious. Sometimes there's gonna be problems, the beginning ones, they're gonna be like, yeah, I know it's gonna go to the right, I know it's gonna go to the left. But as we get further along, they get a little bit more complex and they go, you know, the applied loads goes in various directions and it might not always be obvious. So I'll let you in on how you know if you assumed the correct direction or not. There's a definite way to determine that. So number 2 is we are again going to use the equations of equilibrium to solve for any of these unknown applied loads and reactions. So equations of equilibrium. And we know those to be the 3 that we have up there. Okay. So any questions so far? Good stuff. That's kind of all what's at the beginning of in the introduction for chapter 4. Okay, in our McGraw-Hill. So let's do a problem. Now I'm going to skip over to the problems. They have some sample problems here, but I don't know. I kind of like, I want to start on a little bit. I want to throw you a softball, not a hard ball just yet. Okay. So we're going to look at problem number 4.2 on page 174. So that is this problem right here. Okay. This problem right here. And the problem statement says we have a 2,100 pound tractor. That's going to be the weight of the tractor. Is used to lift a 900 pound load or pounds of gravel. Okay. And that's going to be in the scoop here. Determine the reaction at each of the wheels in the rear and in the front for this tractor. Okay. So what we're going to do is we're going to draw first a free body diagram to simplify what's going here. And it's not even going to look like a tractor when we're done with it. We're literally going to draw a straight line from A to B and then to the very end, and that's it. And the reason we can do that is we're going to find that all of our forces are vertical, so we can move them along their line of action. And we're still going to represent it with the, it's still going to have the same net effect on the body. Do you remember what that's called? The principle of transmissibility. Yeah. Have you told anybody? You know what I learned today? We've been talking about the principle of transmissibility, just so you know. And then does anybody go, wow, that sounds hard? You're like, yeah, it is. It is. Can impress people with what you're doing because it is impressive. So that's what we're going to do. We're going to draw the free body diagram here. So we'll do this together. So at the top, it says, let's work this problem. So free body diagram and convention first. So I'm simply going to draw, like I told you, straight line. Okay. Straight line, put my convention in the upper right-hand corner here. And as I look at my tractor, I've got A on this end. I've got B, and then I'm going to call C where that 900 pounds is coming down. So one end is going to be A. The other end is going to be C. And then B is a little bit more than halfway. Okay, call that B. To just kind of get started. Now, applied loads that we can see on here. I always like to do applied loads first, and then I'll go back and do my reactions. It really doesn't matter which order, honestly. I've got an applied load of 900 pounds, okay? And in my problem statement, it told me that my tractor weighs 2,100 pounds. So at the center of gravity where G is, we are going to concentrate that 2,100 pounds going straight down because that's the weight of it. So I'm going to start with my 900. Oops. Straight line. So this was 900 pounds at C. And then at G, right about, I don't know, here-ish, I guess, right? G, we're going to put 2,100 pounds. I'm just going to have it going up. Whether you put it at the top of the line or the bottom of the line, doesn't really matter. Now I can add my distances that I have kind of these things in here. So this is going to be 20 inches 40 inches and 50 inches. Okay. Now the last two are going to be my supports. So these are what we call the applied loads, the weight of the tractor, 2,100 pounds, and the 900, which is the weight of the gravel that we're scooping up. Now we're going to put in our reactions. Those are at A and B. And if we look, they're wheels, right? They're wheels and they roll. So if we go back to page 160, do you see how it's going to be a roller? Okay, for each of those. Now, remember, there's going to be one force perpendicular to the surface we're riding on. So as we look here, our wheels are on horizontal surface. So that means that we are going to have forces that are going to be perpendicular to our surface. Now, arrowheads, as we look at the applied loads, okay, both of those forces are going down. And now we have two supports that we need to put our arrowheads on. Up or down, do you think? Again, we may not know confidently, but we may have an idea, but we have to pick a direction no matter what. You can't overthink this. I just need one force. Do I want to go up or down? What do I want to do at A? I'm going to go up on A. Okay, that sounds good. What about at B? Up, sure, let's go up. And then what I'm gonna let you know when we know if we assume the right direction. It'll be right at the end. Okay. I know. I'm getting excited. It's gonna be good. All right, free body diagram questions, anybody. So this is our step number 1, free body diagram. Important that you draw it sizable, make it large enough so that you can make the notes on here and you can make sense of it. Okay. You don't have to fit it into a little corner. So in step number 2, as it says up here, we're going to use our equations of equilibrium to solve for the unknowns. So I'm just going to write them out here. My options here are sum of the forces in the x equals 0, sum of the forces in the y equals 0, and some of the moments around a point have to equal 0 once I identify that, right? So I got to decide where I'm going to start. If I just start with sum of the forces in the x, that's going to be when I have unknown forces or any forces in the x direction. Do I have any? I do not. I do not. So in this particular problem, we're just not going to use this equation. We may not use all of them all the time. It just happens to be that there are no horizontal forces here. So that means that we're not going to use that one. But we do have vertical forces. Actually, all the forces are vertical. So some of the forces in the y is going to be in the play, and then also moments. We're going to use these two for this one. So let's start with some of the forces in the y. Now remember, when we're summing our forces in the y, we're in, like I say, force mode. So we're going to go to our convention, and anything that is vertical will be positive, and anything that is, anything that is going up vertically is going to be positive. Anything that's going down vertically will be negative. So as I look here, I'm going to set this up. Sum of the forces in the y equals 0. My left-hand side of my equation is going to be exactly that, summing my forces, looking at my diagram and identifying positives and negatives. So as we look, going left to right, I've got a positive A minus 2,100 pounds, it's going down. I've got a positive B going up, and I've got a minus 900 pounds going down. As I look, that exhausts all of the forces that are along my beam. So now I'm going to set this equal to 0. Make sure you do that. Remember, this is an equation of equilibrium. I need an equal sign and I need two sides. Okay. Don't just like randomly add it on step number 3 or something. Okay. I look for that, and you will lose points if you don't have the equal to 0 there. Now I look what I can combine. Looks like I can combine these two, right? So I'm going to have A plus B minus 3,000 pounds is equal to 0. And I have two unknowns, but I'm going to clear the negative. I'm going to put the 3,000 to the other side. So I can say A plus B is equal to 3,000 pounds. Okay. So I have to stop there. I can't go any further with this one equation, right? Don't worry. It's not going to be 2 equations, 2 unknowns, I promise. But what we are going to be able to do is solve for one of the variables in our next equation, and we're going to use our moment equation. Okay. Now I'm going to leave a little bit of room here. And we're gonna say, we're gonna sum our moments equal to 0, but we're not done with this equation. As we look above, the two unknowns that we have are A and B. And as you know, if I sum around a point, anything that's on that point is going through the point and not causing rotation and won't be included in my moment equation, right? Because there has to be an offset distance. So for instance, if I put my finger on A, does the force at A cause rotation? No, no. If I put my finger on B, does B cause rotation? No. So as you can see, I want to strategically place it on one of my unknown variables because it takes it out. And that way, when I put my finger on A, where's my unknown? It's only at B, right? Because this one's known and its distance, and this one's known and its distance. B's distance is known, but not its magnitude. So its magnitude becomes the only unknown in my equation. I can do the very same thing by going around B for A. If I go over the top of B as my point, now A is my unknown variable. I know its distance. I know 2100 and its distance, and I know 900 and its distance. So my only unknown becomes A. Do you see that? So when you have two unknowns like we do here, which is fine, just make sure when you do your moment equation, you pick one of those two to sum your moments around. Okay, so let's sum around A. Okay, let's sum around A. So you might make sure that you identify the point that you're going to sum your moments around. And then we're going to put our finger on A. And then we start left to right. At least that's the order I'm going to go in. And we're going to then sum our moments. So we're going to notice that we're going to have 2100, going to cause rotation. Its perpendicular distance is 20 inches. Okay. So we're going to start down here. 2100 pounds times 20 inches. And then the sign out front, when I put my finger on A and I rotate in that direction, it's going to go clockwise. So that means there's going to be a negative out front. My next one, go back up here, finger on A. I've got B. Okay, B times its perpendicular distance is 60. Do you see that perpendicular distance? So it's going to be B times 60 inches. And then you're going to notice that it's going to rotate counterclockwise, so positive out front. Okay. And then I've got one more force on the end, my finger back on A, pull in the direction of the 900. So I'm going to have 900 times its perpendicular distance of 90 and 10 is 110. And it's going to rotate clockwise. So I'm going to take my 900 pounds times 110 inches. And I'm going to put negative out front because it's going clockwise. Now, as we look here, this is our sum of our moments around A on the left-hand side. Set it equal to 0. So you have an equation with something to solve for. Don't stop here and just start solving, all right? Points off. You have to have equal to 0. And we'll notice that my only unknown here is B. So I'm going to do my math and I'm going to solve for B. Go ahead and do that. I usually use symbols to save space, honestly, because otherwise it starts to get too long. And then I'll usually start writing them out. So if you wonder, like, why does she kind of mix? That's the reason. That's the reason. And if you use the symbols throughout, that's okay. It's no problem. I don't mark that wrong. Then I'm going to combine these two. So I'm going to have negative 141.123 pound inches plus B times 60 inches to 0. And then put that to the other side. B times 60 inches is equal to 141.23 pound inches. And then Now, when I divide by 60 inches, by keeping my units in here, you'll notice that my units cancel inches wise, and I'm left with pounds for the magnitude of a force. This lets me know what? I set it up correctly, right? I'm ending up with the correct units. So make sure that you're putting your units in all phases and then canceling and combining as needed. So my B is going to be equal to 2,350 pounds. Did you guys get that same number? I think it sounds right. Now I'm going to put a box around this. Now, notice something about my value. My value came out to be a positive number. It's not positive in the final answer because it's going up. This happens to be going up, but having a positive final answer tells me I assumed the correct direction. If I end up with a negative value as a final answer, if a negative hung out here and I wasn't able to cancel it, that would mean that we assumed the wrong direction on the start. Okay. And I'll show you examples. I'm going to intentionally do that in a place or two so you can see how to handle that. But our final answer will let us know. So again, sometimes you may not be sure if A or B is going to go up or down. But if I end up with a positive value as a final answer, I know I put B in the right direction. Okay. That's my no, whether it's up, down, left, right. I know that direction was good. So I'm just gonna label this 2,350 pounds. You don't have to put that on the diagram, but that way you just kind of know. Okay. Any questions so far? I'll go back down here just in case anybody needs to catch up. Just look in the chat to be sure. Up. Okay. Thank you, John. You got it. You got it. All right, now that we know B, we can go back up to some of our forces in the Y, right? And we can use this B to solve for A. So now we can say A plus 2,350 pounds is equal to 3,000 pounds. So A is going to be equal to, and I'm going to subtract my 2,350 on the other side. And A is going to be 650 pounds. It also ended up as a positive value. So the direction that we assumed to be up at A is correct. Okay. So this is 650 pounds. There we go. Equilibrium of a rigid body. Questions on this problem? Okay. All right, I'll just kind of go here, make sure everybody's got what they need. So we start with a good free body diagram representing first our applied loads, making sure we have our units, our magnitudes, arrowheads on forces have to be. And then we put in our reactions, our reactions at our supports. So identifying, are we rollers? Are we pins? Are we fixed supports? And then putting the appropriate number of supports in place. In this case, there was 2 rollers, so 1 for each, and then assuming a direction. And then once we go through and we use our equations of equilibrium, getting a positive value, we'll know if we assumed the correct direction or not. Okay, if we get a negative, we just didn't. That's okay. Questions? All right, let's do another problem. I'm getting good at this. Problem 4.3. This is problem 4.3 on the same page, just below it. And this is going to be, we have a gardener. And it looks like she's lifting a wheelbarrow that has some fertilizer in it. So it says that the gardener uses a 60 Newton wheelbarrow. That means that that's the weight of the wheelbarrow. Okay. And she's using it to transport 250 Newton bag of fertilizer. Okay. That's going to be the weight of the bag in the wheelbarrow. What force must she exert on each handle? Okay, so you'll notice here that we have the arrangement where she's lifting, it's 0.7 meters to where what would be the centroid or the weight that they're concentrating the weight of the fertilizer bags down. Okay, so we see that force of 250 newtons. And then you're going to notice that between there's 0.15 meters, and then they have the 60 newtons. That means that that is the weight of the wheelbarrow. So that's at the wheelbarrow's center of gravity. And then we have the wheel itself. Okay, that's going to be another support. There's two supports that we have here are her holding it up, and we have the wheel. Okay, now the problem doesn't ask us to do this, but I'm going to have you determine the reaction at both supports. Okay, her supporting it over on the right, but then also what is the support at the wheel? Okay, how we're going to represent this is we're just going to draw a straight line through A. It's going to end at where she would be holding straight down. And because she's holding in a vertical manner, we can move that along that line of action and we can represent it along that same line. Okay, so free body diagram is going to be very simple. I'm going to start with our convention up here. Oopsie. Free body diagram is simply going to be a straight line. Okay. This is going to be, we're going to call it A. They don't really label any of the points. We're going to call this A. We're going to call where she's lifting B. And then we've got two forces in between. So we've got the 60 newtons and the 250 newtons. And those are both going to go down as shown, but they're weights. This is 60 newtons. And this is 250 newtons. Okay. This is 0.15 meters between A and the 60 newtons. 0.15 meters between the wheelbarrow, the 60 and the 250 newtons, and then 0.7 meters between the 250 and point B. So these are what we would call our applied loads, and their distances and magnitudes and directions. So 0.15, 0.15, 0.7. And that goes along with what we had gotten in our problem. Okay, so here's our point A. Oh, I guess they do identify it in there. A, then there's 60, 250, and then the support here. And you could show it at an angle if you wanted to, but remember, everything is perpendicular distances. We would need to know the horizontal distance anyway. So we can simplify it here. Now, supports. The two supports are going to be her lifting and then the wheel in the front. Okay, so for the wheel in the front, that's a roller. And according to page 160 at the very top here, a roller is going to have one support and it's going to be perpendicular to the surface it's riding on. The surface it's riding on here is horizontal. Okay, so we're going to put force, and I'm going to assume up. Okay, and I'm just going to simply call this A. We'll call it AY. We'll call it AY. It's in the Y direction, and we've got point A, so we'll call this force AY. Now B, she is simply lifting, okay, we're going to assume a straight vertical direction, and it's only one force because she's just holding it, right? So we're going to do that very same thing at B, and we'll call this BY. So it looks like we have our applied loads that we know. We have our supports identified, directions and labels and dimensions, and we got our convention in place. So I think we've got a complete free body diagram. Okay, now we're ready to solve for our unknowns. Our unknowns are going to be AY and BY. Okay, of the three equations of equilibrium, which two do you think we're going to use? Sum the forces in the Y, yes. And sum of the moments. What happened to the X? There's no X forces here, right? Yep, so we don't need to worry about that one. So we're going to use the two equations of equilibrium. All right, so where do we want to start? Which one of those two equations do we want to start with? Sum of what? Sum of the forces in the Y. Yes, thank you, thank you, thank you. So we're going to sum the forces in the Y. So sum, make sure that you draw it as the summation symbol, capital F sub Y. Equal to 0. It's like you're telling me what you're going to do. This is the equation in variable form. Now, starting on the left-hand side, We're in force mode, so that means that anything that is in the vertical direction, anything going up is going to be positive, anything going down is going to be negative. Write the left-hand side here based on what we have drawn above. Okay. So as we look vertically here, left to right, I'm going to start. I've got a positive AY because it's going up. I assume that to be the direction. So positive AY. Then I've got a negative 60 newtons. Make sure you put your units in. I then have a negative 250 newtons. Both are going down. And then I've got one more that's going up plus BY. That's the left-hand side of my equation. I summed my forces in the Y direction and I set that equal to 0. Okay, make sure that you do that. Now I'm going to do some combining, right? I can combine my 60 newtons and my 250 newtons. So I can say AY, I'm going to say plus BY minus 310 newtons is equal to 0. And then to clear that negative, I'm going to go AY plus BY is equal to 310 newtons. When I move to the other side, it becomes positive, right? That's as far as I can go on this one. That's okay. I'm going to leave a little bit of a space and we're going to use our second equation. So sum the moments, right? And I'm going to leave a little space here, set equal to 0. Now, I need to identify the point that I'm going to sum around. I have AY and BY that I need to solve for. What 2 points do I want to focus on strategically in order to solve for an unknown, either AY or BY? What do I want to sum around? What or what? A or B, yeah, and A or B because my 2 unknowns are at A and B, right? So if I put my finger on A, it's going to be to solve for BY as my unknown. If I put my finger at B as my pivot point, then it's going to be AY as my unknown. So fill in whatever you want to put there and see if you can write the left-hand side of that equation, and then we'll go over it together in just a bit. If you don't feel confident or you get stuck, don't worry, we're going to go over it together. I'm going to go around A. So if you wanted to go around A to match me, that's fine. Either one though, both of them are valid. And you would get the same answer for the opposite variable no matter which way you do it, as long as you do it correctly. All right, I changed my mind. We're going to go around B. If you went around A, that's okay. Actually, I'm kind of doing this on purpose. If you went around A, you would have solved for BY. Okay. I'm going to go around B and we're going to solve for AY because I'm going to show you that no matter which way you do it, you're going to end up with the same answer. Okay. So I'm going to go around B. I'm going to put my finger on B so that BY is out of my equation. And I'm going to start from the right and I'm going to work to the left. So 250 is my value. It's going to cause rotation. And I'm going to say, and I'm going to do around B, 250 newtons times perpendicular distance is 0.7 meters. And the direction of rotation is positive. So put a positive out front. Okay. Put my finger back on B. And I'm going to go 60 newtons. That's going to cause rotation as well. 60 times 80 or 0.85 meters. 60 newtons times 0.85 meters. And it is also going to rotate counterclockwise, so it's going to be positive. Okay. And then my last force is my AY. Finger on B, go in the direction of AY. That is going to be 0.7 plus 0.3 is going to be 1 meter. So this is going to be AY times 1 meter. And it is going to rotate clockwise or negative out front. Okay. I set that equal to 0. Now I'm going to combine what I can. And then I'm going to solve for AY. 257. Okay, so I go to the other side, it becomes negative. These both become positive, and I divide both sides by 1 meter. Meters cancel, I end up with newtons for a force, which makes sense, right? So AY is equal to 226 newtons. Okay. Now I ended up with a positive value, so that means that I assumed AY to go up. That confirms that my assumption was correct. Okay. Now, what we're going to do is we're going to take this AY and I'm going to put it up here. Okay. So I'm going to put my AY up there. That's 226 newtons plus VY is equal to 310 newtons. I'm going to subtract 226 from 310. And I'm going to get VY is equal to 84 newtons. So if you did sum the moments around A, did you get BY equal to 84? Yes. If you summed around B with me, then you got AY here. But then if you did the BY first and you solve for AY, then you should have gotten the 226 up in the sum of the moment, well, sum of the forces in the Y, right? So I just wanted to show you that no matter which way you do it, whether you go around A or B, you will end up in the end with the very same answer. So if, for instance, you're working with a classmate and you're comparing like how you did stuff, if your final answer is correct, whether they did it around a different point or in a different order does not make a difference. And as long as you both did it correctly and assumed equilibrium in both cases, you're going to still end up with the very same answer. Okay. Makes sense to everybody? Any questions about that at all? I'll leave this up here for just a second in case you need to, get those down.